Hello everybody, Mr. Murillo here. I hope everyone's doing well and making the best out of our days off from school. Anyway, I was wanting to try to move on and kind of go back and retouch on some stuff I know that Miss Sink had touched on with you, but I thought, maybe I could take it a step further, kind of up your knowledge on it or whatever. I'm going to go through a PowerPoint here that I have set up on plate tectonics and on the Earth's changing crust, just geology stuff in general. You don't have to take notes or anything like that. If you look, I'm going to be sending you a link to this PowerPoint so that you'll have access to it. And any of the videos or things like that are linked to it, you can go back and watch those by obviously just clicking on the PowerPoint itself that I send you a copy of. Other than that, let's go ahead and get started. So geology, what? I love to study geology. Hopefully you feel the same way as these people. You're as excited as they are. So to start off, let's talk about Pangea. Now, most of you guys have heard of Pangea before. You've probably learned about it in other science, maybe geography classes. The Pangea, that word actually means one continent. And all Pangea is, it's a point in time in history where all the continents were connected together. If you look here on the right, you can see kind of what it looked like. And here on the left, it shows you, if you look at our modern continents, our modern countries and things like that, you can see how they would all kind of piece together. So plate tectonics is a theory, and it talks about that the crusts are made out of plates that move over time. We call that process of moving over time continental drift. Again, continents moving on the plates. You can kind of see how this works down here. If you notice in the bottom corner, it's showing you how many millions of years it takes for this process to happen. And it's basically starting from millions of years ago in the past and working up to where our continents are at modernly or presently at. This picture up here kind of shows you where all the plate boundaries are. Of course, a little joke, haha, bro, do you even drift? Alfred Wegener and the theory of plate tectonics. What's up, my peeps? My name is Alfred Wegener. In my lifetime, I worked as a meteorologist and an explorer. During my time exploring, I helped to make and used many maps. When looking at these maps, I noticed something that was pretty sweet. I noticed that the continental shelf of the Americas fit closely to Africa and Europe, and Antarctica, Australia, and India, and Madagascar fit next to the tip of southern Africa. They reminded me of the way puzzle pieces fit together. If we move the pieces together, they would look like this. So if you notice in the image over here to the right, you can see again how those continents would be, if you went back in time, how they kind of fit together. Think about 150 million years ago. This is what everything would look like. Now the yellow dot itself is located around where New York would be in that area. So, you wouldn't be a whole lot further from that according to this picture. This led me to the theory of continental drift in 1912. When I told others of this idea, they thought I was crazy. It wasn't until many other discoveries were made by other scientists that my theories was proven in the 1950s. Anyway, I'll let Mr. Murillo fill you in on the rest of the theory of continental drift and plate tectonics. So we have three main pieces of evidence we use to support continental drift. The first over here, continents fit like a puzzle. We've kind of discussed that already. Another one is we find same fossils on different continents that are extremely far apart from each other. We also find similar rock formations that are no longer connected together. So let's take a deeper look at this. To start off with, evidence for continental drift. Continents fit like a puzzle. We kind of discussed that already. You can see the different continents up here, and you can see how they all fit together. Now, it's not like perfectly together, but if you could see the continental shelf, you would see even more so how well they fit together, which is it's pretty tight fit. Some more evidence for continental drift is we find similar rocks and mountains that formed at the same time but are on separate continents. We can also see ice age scrapes in warm areas. So let me cover the Ice Age scrapes first. Areas that you wouldn't normally think of as having like big, huge chunks of ice on them at any point in time, say like, get down into further in the U.S., maybe from like West Virginia on down, we see these big scrapes and these big cuts that we know probably happened during an ice age. Now, obviously, if you're going to have big chunks of ice that are heavy enough to cut into the rocks, you would have to have some pretty cold areas for that to happen. So it shows us that a lot of the continents and stuff during these ice ages were probably somewhere closer to the northern or southern hemispheres of our Earth, as opposed to being, right there where they are now. Especially, think about Florida being, right there at the subtropical line and stuff. And to go back and talk about similar mountains and rock formations, let's use our Appalachian Mountains, for example. If you look right here, you can see the Appalachian Mountains run basically from Georgia, all the way up through West Virginia where we're at, all the way through New York into Canada up that way. But the ironic thing is that we find the exact same rock formations over here along the British Isles. Think about Ireland and England and all the way up into Scandinavia. Maybe you guys have seen videos of Ireland on TV. Or if you haven't, maybe look up one on YouTube. And if they're showing outdoors, you'll see that it looks almost exactly like it does here in West Virginia, the landscape does. And that's part of the reason why. This mountain chain all formed at the same time. And so it's all experienced very similar weather and erosion, even though they're apart now. So when you look, our mountains have weathered down to just the hills that we know today. We see the same thing all the way up through here. Another bit of evidence we have for continental drift is that we find the same fossils on different continents. So think about this, for example. Look here in South America. Let's just follow this plant fossil, for example, that runs right through here. Think about South America and Africa. With their modern continents where they are, they're thousands of miles away from each other. For us to have a plant here in South America and have that same plant in Africa and down into the Antarctic and into Australia, that just couldn't happen. These continents are so far apart from each other, there's no way that plant, the seeds, could have made it to these different continents. It just couldn't do it. But yet we do find, evidence of these plants on each continent. We find fossils. Same thing for a lot of these animals. Look here, with this Jurassic animal here. I don't even have Lystrosaurus, I guess. If you look, you find it in Africa. Here, you also find it way up here in India, which is far away from Africa. You also find it down into Antarctic. These things just couldn't happen. This animal, none of these animals for that matter, could have swam the vast distances between these continents to live on both. And we see certain things like that in America too. We'll talk about that here in a moment. So when we talk about plate tectonics, what actually causes these plates to move? Think about it for a second. If you got any ideas, let me know. Well, first, let's start by reviewing our different layers of Earth. So what is the first layer of Earth, number one, called? If you said the crust, you'd be correct. What's our second layer called? It's the mantle. Our third layer, outer core. And our fourth layer is the inner core. Hopefully you got all of those. So it's important to know the different layers of Earth as we start to talk about how the plates move. So think back to class when we had the lava lamp set out talking about convection currents. If you remember with convection currents, hot rises and cold sinks. So think about the hot wax at the bottom near the lamp, how it floated to the top, and the cooler wax at the top would sink back down. Same thing goes on here. The core, it heats the warm, soft mantle, causing it to rise. Now remember, the Earth itself is made out of rock, but near the core it's so hot that it causes that rock to become very soft, and in some cases liquid. And due to that, it kind of can flow. And so what happens is, if you're nearer to the core, the rock's warmer. And just with their convection currents, that warm rock starts trying to work its way up into the mantle. And as it does that, it pushes mantle pieces around. And as it pushes that, the continents that are on the crust, where it's really cool, slide right along with that mantle as it starts to move. Look over here, for example. We can see this process happening. Notice down here where the core would be, we get this hot magma that starts to flow up. And as it does, it starts getting near the surface and it pushes. And you can just see these loops going on. And what happens is it pushes the overlying crust in the direction that the flow is going. So notice this one's going this way, this one's going this way, and as it does that, you can see how this rock is moving this way and how this crust is moving this way. So because of this movement, we have different what we call plate boundaries. Plate boundaries are basically where the Earth's crust either comes together or it's pulling apart or moving in some way. So first, let's look at what we call convergent boundaries. Notice convergence in green. It corresponds with the green arrows down here. So in convergent boundaries, plates move together. We call that compression or compressive forces. See how these up here showing it moving together? Now what happens is when we have plates that come together, it forms mountains. So these plates start pushing each other, and since they're pushing on each other so hard, the rock has to go somewhere. And what ends up happening is the rock goes up in the air, as you can see here, and it forms rocks. You can also see that process happening here, like you can see the ripples starting to happen in the land. Now what ends up happening in this process is one plate eventually goes under the other plate. We call that a subduction zone. If you look here, you can see your subduction zone happening here. You can also see it happening here. This plate would rod back down and work its way towards the core, only to have itself loop back around and come back up again later on. This process happens very slow, by the way. The crust itself only moves maybe an inch and a half a year tops, maybe 2 inches. But when we have the compression forces coming together, those convergent boundaries, that's where we find mountains. Think about here in West Virginia, the whole Appalachian Mountains. That's how they formed. We had two plates that come together and they squeezed really tightly and forced that top layer of crust way up in the air. The Appalachian Mountain Chain is a very old mountain chain. I've been taught that it's one of the oldest that there is, that it's been, it's maybe the third or fourth mountain chain that actually formed. I would have to look that up and see again to tell you exactly which one it was, but it's very old. So, even though we don't really think of mountains per se, we have more like hills and that kind of thing, it was very tall at one time. It was so tall that probably most of the mountains in our region were snow-capped throughout the year. So anyway, convergent boundaries where these plates come together.